Hi, I'm Tony, and I work on Swift at Apple. At ServerSide.swift 2022, I had the privilege of announcing a new direction for Foundation right here. At first, it was some slides, some promises, and an invitation to the forums. As of about a week ago, that new Foundation has actually shipped in Swift 6. Yeah, I know, great news. Yeah. In addition to actually shipping, we formed the Foundation workgroup, including members from outside Apple, and the source is available on GitHub. So today, I'd like to talk about how we used Swift's interoperability features to make it happen, and talk about what's next. So Foundation is a large project with lots of history and requirements for compatibility. It's also constantly updating and evolving. Because of Swift's ability to seamlessly work with C and Objective-C, we were able to refactor it in a way that allowed us to use Swift at the core of its implementation, giving us more cross-platform compatibility, memory safety, and better performance. Now, these requirements are hardly unique. I'm sure many of you are thinking, that looks a lot like my project. So let's go into the details on how this works, because I think the lessons we learned can apply to you as well. So let's start by looking at the architecture of Foundation before Swift 6. Perhaps you've seen a lot recently about Swift being the best choice to succeed C++ and Objective-C and C. And yet Foundation is the canonical Objective-C library, the first one, in fact. Now, much of the functionality it provides is useful regardless of what language you're using, what platform you're running on, or even what kind of app you're writing. And consistent API is one of the most important characteristics of a first-class cross-platform language. We have the standard library, of course, but it's a small one focused on support for core language features. In that way, Swift can be as narrowly scoped as needed for some environments, like embedded, but still have higher-level features available when you need them, just one import away. So when Swift was open-sourced with Swift 3.0, Foundation's API was brought to other platforms via the Swift Core Libs Foundation library. And this is the beginning of having two Foundations. It didn't seem like the right thing to do to bring Objective-C to another platform when we're here trying to replace it with Swift. However, starting completely from scratch and sharing nothing would have created a really large inconsistency right from the beginning. Now, on Darwin, Foundation has a significant part of its implementation written in C, and that library is called Core Foundation. One of the great features of Swift is its ability to cleanly interoperate with C and Objective-C. And we're going to go into today how important this was, how this turned into the ability for us to meet our parity goals. Swift Core Libs Foundation took advantage of this to reuse Core Foundation's C code. And since Swift was not yet ABI stable, a Swift overlay was added on top of Objective-C and provided specialized Swift API. Some of that code could be shared with Swift Core Libs Foundation. However, both the C and the Swift code were copies, specialized for each platform. And here we have the shape of what we shipped from Swift 3.0 to Swift 5.6. Now, the most astute among you could perhaps see where this could start to go wrong. Once per year, when a new version of Core Foundation was released, we would attempt to sync it up with the one in Swift open source. And it was a complex two-directional merge that I think we only managed to do 2 or 3 times. And there were a lot of open questions. How does new Swift code from Darwin get to open source? What if it was an Objective-C type brought into Swift via the importer? Would we have to re-implement it in Swift, but only for other platforms? How would we keep those in sync? And what if a contributor implemented a new Swift feature, and would someone have to re-implement it, but in Objective-C for Apple's platforms? And so the inevitable consequence of a fork eventually catches up with us. Too many changes in too many places, and some kind of tragic merging deadlock. But all is not lost. It was time to untangle this mess for the benefit of not just those of us that had to try to work on this spaghetti, but for the benefit of the entire Swift ecosystem. So let's set out some top-level requirements. First, we need a structure that enables real open source contributions. This fundamentally means shared sources, not two-way merges. We also must maintain compatibility with existing sources and binaries. It would have been far easier to reinvent all of Foundation's API from scratch and then encourage everyone to move over. However, it just gets us right back to the two of everything problem we were trying to get away from in the first place. And finally, we should use Swift. Maybe it's obvious, but why? Well, Swift has a lot of advantages for real-world large projects like Foundation. Projects that want to move away from C to a modern, safe language, but can't do a big refactor all in one step. First, it's ABI stable, so everyone's favorite apps keep working. It has the built-in interop that we've been talking about with other languages like Objective-C, C, and C++. A focus on performance means that the most commonly used APIs can also be the most efficient. And finally, since Swift is a safe language, those APIs can also be the most secure. So with those advantages in mind, let's revisit this assumption that we should build the new stuff on top of the old stuff. Does it have to be that way? Can we do the opposite instead? And can this application up here be none the wiser that we've completely changed the implementation underneath it? Well, first, with ABI stability, we can use Swift inside Foundation Framework itself and eliminate the overlay. And we shipped this in macOS 13 Ventura and other releases in the fall of 2022. This small step was important because it got the sources for Swift and Objective-C into the same binary. We proved that we could build all of Apple's OSs this way and keep Objective-C and Swift apps working normally. Next came the fun part. Can we be writing Swift instead of Objective-C? And the answer is yes. We'll have Objective-C call into Swift instead of the other way around. Let's go one step more. Can we be writing Swift instead of C too? And the answer is yes again. And this is what we shipped in macOS 14 Sonoma and other releases in the fall of 2023. Key types like calendar, time zone, and locale were rewritten entirely in Swift. We then deleted the C and Objective-C implementations, all while maintaining compatibility with existing apps. Here's how it works. In Core Foundation, we define CF Calendar to be a pointer to a new NS Calendar subclass. We then use Objective-C to trampoline into Swift. In Foundation, we use that same Objective-C method to get the current calendar in this example. And in Foundation's Swift, we implement that method with the obc attribute. Both the C and Objective-C are using this thing called NS Swift Calendar. This subclass wraps the Swift struct. And in its override of the NS Calendar methods, it does any kind of argument fix-up as needed. And finally, this calendar is the same one you would use directly from Swift. So in this way, all callers from C, Objective-C, and Swift all funnel through to the same Swift implementation. By the way, even though this shim code is only for Darwin, the Swift part is actually available in our GitHub repository if you want to dive into some more details on how all of this works. Now, we found this pattern to be really useful. So, if you're building a library and you need to maintain compatibility with existing clients, you might also be able to try this approach. Rebuild the old stuff on top of the new stuff, one part at a time. At the end of the day, this means that the critical code is written in Swift instead of C. Another benefit is that the calendar type can have API that is just for Swift, API that takes advantage of idiomatic features of the language. For example, this new function for enumerating dates is available only in Swift because it uses features like ranges, generics, sum types, and sequence. As more code that uses calendar migrates to Swift, these APIs become available to them and are a more natural fit. So now we've accomplished two of our major goals: use Swift and maintain compatibility. Our oblivious application is blissfully ignorant that we have completely shifted the ground underneath them. For Swift 6, we turned our attention to the next goal, enabling open source with shared code. So let's return to our Swift 5.9 setup. Here's Foundation on Darwin, and here's Foundation on other platforms. Visualized on a slide like this, the answer seems obvious, right? Use Swift and build the old stuff on top of the new stuff, and minimize the amount of C. Swift is better anyway. We stop attempting to sync up the C code for two reasons. First, on Darwin, it's moving more towards becoming a shell that simply calls into Swift, as we saw. And second, on other platforms, we want to replace it with Swift completely. And this is what we shipped this year in macOS 15 Sequoia and other releases, and Swift 6 for all platforms. Finally, we wanted to address one more common request from our server-side developers. Many apps would like to use fundamental foundation types like URL and JSON decoder, but don't need all of the data that comes with Foundation's internationalization features, like localized formatting. Foundation on Linux has, for some time now, split itself into a few libraries: Foundation XML, Foundation Networking, and Foundation. And this is because of the dependencies of libxml2 and libcurl, which could be pretty large for some apps. In Swift 6, we divided it one more time into Foundation Essentials and Foundation Internationalization. Using the Essentials library when you don't need any of the higher level features creates much smaller binaries. These libraries are organized into two GitHub repositories. Swift Core Libs Foundation is now focused on being only for non-Darwin platforms and is built on top of Swift Foundation, which is our cross-platform shared Swift code. And that is where we expect most future development to be. Okay, well, that was a lot of boxes. So what did all of this refactoring get us? Well, using one Swift implementation allowed us to completely rewrite many of the most commonly used types in Foundation and share them everywhere. In addition to calendar and locale, we rewrote the JSON parser, string comparison, string encoding conversion. Then we re-implemented URL and URL components, file manager, process info, the property list encoders, data I/O, base64, and much more. We were also able to bring a huge amount of new API to Linux. Some of these, like format style, locale components, predicate, and others, have shipped before, but only on Darwin. Others, like the new expression macro, calendar recurrence rules, and future API, now ship simultaneously on all platforms. Implementation upgrades, like using a rope for attributed string, are also now completely cross-platform. Transitioning from C and Objective-C to Swift wasn't only about portability, though. Swift's better performance and focus on compatible interop allowed us to make some pretty impressive performance gains for all clients, even if they themselves are still written in Objective-C or another language. JSON parsing, pretty popular. So here are the results of a benchmark in our new test suite, comparing Swift 5.10 to Swift 6 on an Intel MacBook Pro running Ubuntu 24. Decoding this test data is over 200% faster. Here's another one with a different data structure in the JSON, which is twice as fast. Plus, you don't have to do anything to get this improvement when you're using JSON decoder. On Darwin, these improvements are even bigger, since there we don't have to convert data types between Objective-C and Swift. Some of the performance gains from rewriting URL in Swift are massive. There's a 38 times speedup for parsing valid strings with the basic URL from string initializer. Parsing an invalid string is 128 times faster. And when fetching ranges of a string from a URL components, it is 292 times faster. Yeah. So these examples are interesting. Yeah, thanks. So these examples are interesting because it shows what we can get by using Swift instead of C under the hood. The API is the same, but the implementation can avoid conversions from Swift strings to C strings and vice versa. Here's another one for formatting dates. Before Swift 6, to format ISO 8601 dates, you would use the ISO 8601 date formatter class. Now, one of the pitfalls of this API is that it's really easy to forget to cache the formatter instance. And if you remember to do it, caching and reusing it is better. But now that the format style API is available on Linux, you can use that instead of the formatter. Why? Well, ISO 8601 formatting is important for server developers for things like logging, and it's critical for it to be as efficient as possible. We wanted to provide this functionality without requiring the overhead of our internationalization data. So we completely re-implemented the Gregorian calendar in Swift. And this enabled us to put ISO 8601 formatting, which uses the Gregorian calendar, into the Essentials library. And the new Swift implementation of the calendar is also pretty fast. The first code snippet has a throughput of about 21,000 operations per second. The cached one is better at 603,000 operations per second, but the format style option blows both of those away at a whopping 2.1 million operations per second. Why so much faster? Swift allowed us to easily write code that avoids allocations and conversion costs. And again, best of all of this was done in the foundation that ships in the Swift toolchain. So when you upgrade to Swift 6, it's all included for free. And that is the power of incremental adoption of Swift. You can start small with whatever you can, and then iterate by moving to Swift implementations at the core. And it will only get better over time. So that's a great place to transition to talking about what's next. First, I want to emphasize that community involvement in Swift Foundation has been a huge success. Over the past year, 8 proposals were pitched on the forums and received a lot of great feedback. And those discussions had a direct impact on the API that shipped for Foundation on all platforms. So over the next few releases of Swift, the Foundation Workgroup has decided to focus on 3 initiatives to improve the project and encourage even more community collaboration. First, more Swift. I spent most of my time here telling you what's finished for Swift 6, but despite all that we did, there is more left to do. Foundation is a pretty big project, and so we will continue removing C and adding Swift. Performance work is never done either. We talked about how much faster JSON parsing has become, but we want even more. So we're investigating a new API that takes advantage of language features like deterministic lifetimes and Swift macros. And we would like more benchmarks for all of Foundation's features, especially ones that reflect real-world uses in all of your projects. And finally, we're planning a paper cuts initiative. So paper cuts are small annoyances that add up to a poor experience, especially for newcomers to Swift. This is a place where we really need your involvement and experience. With a significant portion of Foundation's implementation now written in Swift, shared, and open source, this is a great opportunity for the community to jump in. In particular, we're looking for changes which have a high impact but don't require a large amount of new API. To support this initiative, the workgroup is making a few updates to the way we do API reviews. Now, one of the benefits of Foundation being a bit higher level than the standard library is that it should be able to move faster with new API. So we want a process that still ensures quality, but does not feel too heavy for small changes. To help with that, the workgroup appointed one of its members to be an API champion. That person has the authority to accept minor API proposals after a shorter review process. For example, the review might be a proposal document that has a pitch thread with broad agreement. This will make it easier to get small but important features into the project. More details on this new process will be coming soon to our GitHub page. The high-level goal is to encourage more proposals from new contributors. We believe this will help not just the people who use Foundation, but also to grow community involvement in the project as a whole. So with that in mind, I'd like to close with a call for your involvement. Foundation for Linux builds as part of the toolchain. In Swift 6, though, it is now possible to build Swift Foundation and Swift Core Libs Foundation with Swift PM as well. This is dramatically easier than building the entire compiler. On macOS, you can also use Xcode to build and test the Swift Foundation package. This is a great way to just explore how Foundation works if you're interested. Thank you for your time, and a huge thank you to the Swift community for all of the work that you've done to help all of us get this far. I think the future of Foundation looks brighter than ever. Now that I've talked about replacing C, Objective-C, and C++ with Swift, here is Ben to tell you more about Swift and interoperability.
Thanks, Ted. So 10 years ago this month, you were first able to ship an app to the App Store written in Swift. And this was just 3 short months after Swift was first announced to the world. There wasn't yet a Swift community producing the great packages that we all know about today. There wasn't even a Swift package manager. That came later. But from day one, you could be productive writing Swift, because Swift could interoperate seamlessly with Objective-C. This interoperability with C and Objective-C allowed the amazing work Tony just went through to be able to transition a foundational framework to Swift, all inside a shipping operating system, providing APIs with a stable ABI. As the browser company put it in their blog post on swift.org, interoperability is Swift's superpower. But this interoperability is more than just being able to leverage existing ecosystems like the Apple SDK to be able to ship software right away on day one. It also facilitates incremental adoption. Incremental adoption is vital to being able to successfully transition to a new language in an existing code base. Now, there's this joke about a tourist, and he gets lost driving around on holiday, and eventually he sees a local, and he decides to stop and ask for directions, and the local thinks for a second and says, "Well, I wouldn't start from here." Switching to another language in an existing application is a little bit like this. You have this whole body of code, maybe a team maintaining it, and you want to make the switch. And sometimes the answer is, yeah, well, I wouldn't start from here, so let's rewrite the whole thing. And sometimes rewriting it in one go is the answer, but that's actually pretty rare. There are several famous examples of where a big plan to do a full rewrite actually led to a disastrous result. Usually it's better to take an incremental approach, and Swift allowed this from day one with your Objective-C code. You could start your Swift journey with just a single method extending an Objective-C type, and then maybe you could replace an existing Objective-C type, or you could write new functionality in your app in Swift, interoperating with the remaining code in Objective-C. And this isn't just about technology. There's social issues involved here too. So if you take the rewrite approach, it'll probably take a long time, and chances are you've got to keep shipping your existing code. So you have to maintain the old code, and that might end up being twice the work it would otherwise be. And maybe you have separate developers maintaining the old code and the new code. Maybe you separate your team into a legacy maintenance team and a rewrite team, and that can lead to an unhealthy team dynamic. Or maybe you keep everybody working on both, but nobody wants to work on the old stuff. Finally, there's this tendency for these grand rewrites to never ship, because the temptation is to fix all the problems in the old system, do it right this time. So this is why incremental adoption is really important. The whole team can just work on the existing code base and incrementally adopt Swift as you go. New features can be written in Swift. Maybe you rewrite the most important parts to improve performance or correctness, leaving the bits that are doing just fine alone for now. And all of this comes together to show how the entire Apple app ecosystem has been able, over the last 10 years, to transition from Objective-C to Swift. Today, there are 1 million apps in the App Store written in Swift. But we're here at the ServerSide.swift conference, and I'm sure a lot of you care about apps too, but what about servers? Now, some servers are written in C or C++, and Swift interoperability with those languages can give you a path to a safer, more modern language like we just saw, without having to do a whole rewrite. But there are more ecosystems than just ones based on C. Java, or more broadly JVM-based languages, are another important one found in many places, especially on the server. Java has this great compromise of approachability and memory safety that led to really rapid uptake for back-end processing, starting in the 90s. But it's a managed language, and that means performance, particularly memory usage, can be a challenge. Garbage collectors, JVMs, and JIT technology, they've all got pretty good over the last 20 years, but keeping memory use down is still a struggle. Now at Apple, we have plenty of Java server-side code still, serving billions of requests a day, and we've found that migration to Swift can dramatically cut down on things like memory use and server footprint. But at the same time, all of these factors we talked about, the ability to keep using existing code while migrating part of a code base to Swift, is really important. And for that reason, we've started work to bring Java interoperability to Swift. So like all our work on the Swift language, we're going to do this out in the open. And so we invite the community, particularly any Java experts amongst you, to participate in the design and implementation with us. So there's a repo available today under the SwiftLang organization on GitHub, where anybody interested in this project can collaborate. It has an early proof of concept of Java interop working as a starting point, and we can take a quick look at that now. So I'm going to come out of Xcode. Sorry, I'm going to go into Xcode. And we have here some of the repo. So I've checked out the repo that's available on GitHub, and we can look at some of the sample code that comes along with it. So here I have a public class written in Java. So it's pretty simple, has a few fields, has a few methods, and I want to be able to use this code from Swift. So I can switch over here to a file that does exactly that. So we'll see here that it imports two things. So first of all, it imports the Java runtime, and this is the Java project's C headers for providing access to the runtime, in particular, the Java Native Interface API, that is how you interface from native languages like Swift to the Java JVM. Now, this actually provides a lot of pretty nifty functionality. You can, using JNI, access methods, get their ID, and then use that ID to invoke methods on a Java object from your native language. And that's great, but it's pretty fiddly to use. It's not all that enjoyable to write large projects using this kind of technology. But this actually sounds pretty similar to something we know about. Objective-C also allows you to access a method selector and then use Object-C message send to invoke that selector on an Objective-C object. But again, you would never want to actually do that from your code, and that's what interoperability from Swift is all about. It's about making it seamless and easy to get up and running and access the features in another language. And so that's what this second import does. So as part of this repo, we have a module called JavaKit, and that's a selection of tools to allow you to access Java that wraps JNI and makes it a lot more of a seamless experience. So here we have, down here, a declaration of a struct that represents the Java type that we just saw in the other file. And you'll see that if you're familiar with Objective-C interop, it's a similar technique where you put an attribute on the type, and you also use that same attribute on the methods to gain access to them. The one difference here, if you're familiar with macros, is have a capital letter because they are implemented as macros. And this actually makes it a lot more accessible to see what's going on under the hood. So if we expand a couple of these macros, what we can see is that they're using the name of the field and passing that into the JavaKit library, which then accesses the JNI functionality to actually invoke the method. You can expand this one here to see that it's making this call to invoke a Java method dynamically. We can have a quick look at that. And this is some of the code that appears inside the JavaKit framework. If you're familiar with parameter packs, this is an advanced generics feature that makes it really easy to have powerful wrapping functions that allow you to call this method strongly typed with any method types, any method arguments that work in Java. So we can have a scroll down here, and then we get to this implements Java. Now, when you're talking about interoperability, it goes in both directions. So you might want to call Java code from Swift, and that's sometimes referred to as forward interop. But you also sometimes want to call Swift code from Java, and that's sometimes referred to as reverse interop. And you usually are mostly thinking in terms of one of them. Maybe you have an existing Java library that you want to invoke from Swift, and you would think of that as forward interop. But usually you tend to want to use both of these together, because often it's common to create a Java type and then send it into the Swift code and then be able to invoke methods on it from the Swift side. And that's what's happening here. So say hello, we saw earlier. This Java type hello Swift is a class declared on the Java side, but down here we're using JNI's native keyword to say that the implementation of say hello is actually a Swift method. And then inside this Swift method, we have the forward interop techniques where you have access to self, and that self is a Java object, and then you can invoke methods on this Java object directly. And because this is all working in native Swift on this side, code completion works. So we can have that working. If we scroll down, we see that various different things are implemented, including all of the native Java types. We have arrays. There's also an implementation of downcasting, which returns an optional, depending on whether the type is of a particular subclass that you can unwrap using the familiar if-let syntax. And finally, we have examples of catching exceptions from Java that come through as errors on the Swift side. So this is fairly fully featured already, even though this is an initial prototype. And we can actually run it. And here we see the running code going back and forth between Java and Swift. Now you'll see that this was a fairly manual implementation of the wrapper. Obviously, in practice, you wouldn't actually want to have to write the wrapper yourself. So there is a code generator that generates those wrappers for you, kind of similar to how you generate bridging headers if you've ever used Objective-C interoperability. Here we can find the code for that code generation tool, which is also available in the repo. The nice thing about this is that the code generation tool is written in Swift and itself uses Java interoperability. So it's accessing the Java reflection capabilities, which are what it uses to, when you point it at a jar, extract all of the types and the methods on them, and then generate the bindings for the Swift side. This is an interesting case where we're going the other way around. The example we just saw was you fire up Java and then it calls into Swift. This is an example where you launch a Swift process and then Swift creates an instance of the JVM and then invokes all of the reflection methods in order to analyze the jar. If we switch back over to terminal, we can see it running. So here's the Java to Swift program. And what happens is you point it at a particular Java type. So here I'm going to generate the code for a Java URL type. We run that. You get a couple of warnings because there are some features that aren't yet implemented for particular initializers, but most of the code comes through. And if we switch back here, we can see that we now have the import bridged for the Java URL type that is now available to use from Swift. Now, at this point, it's probably worth a little caveat about performance. Java is a managed language. And so it has a virtual machine. It uses garbage collection to track objects. When you send an object from Java out into a native code base, it can no longer manage entirely that object using the garbage collector because it can't see inside that native interface. What needs to be done at that point is that an object needs to get pinned. JNI calls it promotion, which sounds a lot nicer than it is, because it actually can be a performance challenge if you promote too many objects. You usually want to keep the number of objects that you keep on the native side a little bit lower to keep the performance of the JVM itself doing okay. And performance of this particular aspect is going to be a key focus of the development going forward, both making JavaKit better so that it can be smart about only pinning those objects that are absolutely necessary to be brought over into the native land, and also using the features of the Swift language to help developers be mindful of the fact that they don't want to keep a large number of objects alive on the Swift side. This is very different to Objective-C interoperability, where both languages are native and use reference counting, and so could natively use each other's create and destroy methods, and so didn't have this performance challenge. So that's something that people are going to need to be aware of, because if the experience is as seamless as with Objective-C, and that is the goal, then it might be easy to forget that you are dealing with a virtual machine that needs a little bit of care from a performance. So that's bringing stuff over from Java into Swift. What about the other way around? Well, there's a similar technique available there for providing Swift libraries to Java. So here we have an example of a Swift module. It's a JavaKit example. And you see it's just a regular module. It has public methods, and it also has a class in it with properties that you might want to access from Java. And so similar to the previous case, there's another tool that can be used to generate Java bindings for Swift libraries. So I've run that here, and this is also available in the repo. And once I've done that, I now have the ability to access my JavaKit example module. And if we look down here, we see examples of calling free functions, which in Java, because Java is the kingdom of nouns, they have to be owned by a type, so they're static methods on a JavaKit example type. And then you can see an example of creating that Swift class from Java using its init method, passing in arguments, and getting back an object that you can then use on the Swift side. This bridging back from Swift into Java is facilitated by a pretty cool new technique on the Java side called Project Panama that's only available in Java 22. So depending on the version of Java you're going to be able to be operating with, you can either use this technique or you can use the older JNI native technique that we saw earlier. So that is a quick whistle-stop tour of what's available today. We'd love for people from the community to get involved and talk to us about what they'd like to see out of this feature, particularly if you have a background in Java and particularly performance in Java. We'd love to talk to you and collaborate with you on this project as we work on it going forward. Thanks a lot for your time.